Thank you very much. Thank you, Michelle, for the invitation to talk today. In this presentation, first, I'm going to talk about Base CCS because probably you haven't heard about the company. Also, maybe about myself because probably you have never heard about me. About my experience, or the experience of Base CCS with Cape Open, and the motivation of why, at least I think we should do a bit more of Cape Open work within the company and maybe within the CCS industry. What are the current modeling practices that we do in the industry, and what we plan to do on our current model development projects that we have. About PCCS, we're a small consultancy. Well, we're 40 people. We're a specialist CCS and hydrogen engineering consultancy. We have 3 offices in London, Kuala Lumpur, and Houston. We have been working in about 60 CCS projects around the world. And what we do, we get involved in the engineering design from early stages, so that is feasibility, concept, and all the way to fit. We are not an EPC company, but we support EPC contractors. We do a lot of third-party reviews, and we deliver training courses, and we have something that we call a digital twin, which I might show you at least just one slide about that thing. About me, so I'm the technical and operations director of BASE. I'm based actually in London. I've been with the company since the start, so that's 5 years ago. I have more than 17 years of experience in both academia and in industry. I have a bachelor's in chemical engineering, and I did a PhD in Manchester in process integration. Then I moved to Imperial College in the Center of Process Systems Engineering. So that's when I heard a bit more about Cape Open. After that, I work in a number of consultancies, mostly in oil and gas, and I have written some papers on various topics. My main interests are in the area of computational thermodynamics and decarbonization and sustainability. The experience of PACE the PACE experience with Cape Open is that, so nothing really. We don't have anything to show with Cape Open yet. My experience with Cape Open is really as a user only. Back, I think maybe probably 15 years ago, when you are in Imperial College and you're working in the Center of Process Systems Engineering, I think everyone has to work a little bit in the company, or what is called Process Systems Engineering, Process Systems Enterprise, sorry. So everyone has to do a bit of, I suppose you have to spend some time there. So I worked there for a few months, and one of the things that I did, I was doing really some quality control of the GPROM's Cape Open foreign object socket, which, okay, fine. I run cases and it ran. So I think that was the only thing that I did with GPROMs and Cape Open. But I started understanding kind of the benefits of integrating different pieces of software from various vendors. And then after that, some years down the line, I did some work integrating multi-flash, which I suppose you know it, with HYSYS, and this is for a CCS applications, but it was very, very simple, just a compressor train and a dehydration within HYSYS, and run using the multi-flash thermodynamic model as for the physical properties. And that's really my only experience with Cape Open. But I think I just want to talk a bit about what we want to do with this and what is the motivation. This is what we call CCS cluster. Unfortunately, I think I missed the first part of the presentation of Jens that was talking about CCS. So I don't know how much he went into explaining what is CCS, but I'm going to go maybe slightly quick. So we want to capture CO2 from various industrial sources, and that could be a power generation plant or DAC, so direct air capture, or blue hydrogen production, and etc. So various industrial sources, like cement, like the one that also Jens was saying. So we capture those industrial CO2 emissions, and those CO2 emissions is being gathered in transportation systems, normally onshore, and then the CO2 is being further compressed and boosted and sent either for offshore storage via pipelines or maybe potentially exported via shipping. So this is type of systems that we are looking, at least in Europe and in many places. And the reason that we want to do this in industrial CCS clusters is basically because of economies of scale. No? So it gets cheaper for the system to kind of sharing facilities. In the case, like, for example, many oil companies, they have also doing CCS. They are capturing their own emissions. So that's what we call one emitter, one source. So they capture their CO2, they strip the CO2 of the natural gas, for example, and then that CO2 is being piped and sent for permanent storage possibly in saline aquifers. The operation, and I think the modeling of this type of system is almost trivial. And the reason that I think it's almost trivial is because the composition can easily be controlled. So the system can be easy to operate and to the bottleneck. And this is because mainly because the emitter is the owner of the infrastructure and storer. So kind of designing this kind of systems and also the operation of the system is kind of trivial. It's very simple. But what happens is when we have various emitters, so each emitter is going to have perhaps different flow rates. Each emitter is going to have different composition, so different. Even though they're going to be subject to the same specification, they all going to have different composition. So because it depends of the type of industry, of the type of the capture technologies that they have. The other important thing when we design these systems is that if the system we know that is going to start, let's say in 3 years, we know that we're going to have maybe 2 or 3 emitters, but this system is going to be operating for 20, 30 years. So over that period of time, we think that future emitters are going to be tying in. So we need to design the system keeping in mind future unknown emitters are going to be tying into the system. And the most important thing is that the infrastructure, so the transportation and the injection infrastructure, the owner of that and the operator of that infrastructure is not necessarily, and most likely, it's never going to be any of those emitters. So the infrastructure is going to be really, or let's say the CO2 that's going to come into the infrastructure is not going to be really controlled by the operator of the network, and that brings a lot of challenges, not only for the design but also for the operation. And I think also it was mentioned before. So the CO2, when we're talking about CCS or industrial CCS, in reality is never pure. So we never say that we say CO2, but it's never actually pure. So we're gonna have, literally almost every possible chemical compound that you can imagine, depending of what is the source of that CO2. And of course, if you have a lot of different emitters with different, as I mentioned, with different capture technology or process technology, you're going to have at the end in your transportation system a whole cocktail of nice stuff, and you're going to have weird stuff like dioxin sulfurants that comes from cement of waste incinerators, which we're going to have not necessarily an issue for the say for the thermodynamics point of view, but it's going to have an issue for health and safety, for example. No? So when I say CO2, or when we say CO2, it's actually CO2 with a lot of impurities. And those impurities also, as it was kind of mentioned before, it has a lot of effects. Water, for example, which is something that we are very concerned because that leads to corrosion. We have 50 parts per million of water, and this is the blue line. The green line is the due line with that amount. So we specify the water dew point to say minus 30 degrees and whatever 20 bar or 10, 15 bar. But for example, 2,000 parts per million, it just completely shifts the water dew line to the right. So we're operating around this range, which is kind of the operating range gas transportation of CO2 gas transportation of pipelines, this is an issue. Not only that, we know that, for example, depending on the different impurities that we have in the system, if we do have some aqueous dropout, some water dropout, depending on the amount of the amount, but also the type of impurities that we are going to see different corrosion rates. For example, this is a corrosion rate. I think this is a stainless steel with only with CO2, so it's very low. But once that you are having different type of impurities, in this case we have, but not only water, but for example oxygen and H2S or SO2, we have different corrosion rates. Once you have more than 2 impurities, then suddenly your corrosion rates start changing. No, so this is also a complication when we do the design of the pipelines, because we need to know, no, if we are going to have corrosion allowance, or we need to know how many times are we going to see this type of events in which the system is going to be operating in this region. Other important or another effect perhaps is if we have a little bit of glycol. In this case, we have 2 different compositions, and the only difference is one has about, say, 2 parts per million of glycol, and the other doesn't have any glycol. I don't know if you can see the numbers, but essentially in this one, in the cocktail one, we see some droplets of glycol coming out from the CO2 at kind of low, low temperature and low pressure. If we don't have glycol, then we don't see that effect. No, so and then if the problem with the glycol is that it's very it draws water from the CO2, and also that's going to be causing corrosion. No? So and perhaps a most known effect is that these non-condensable, what we call non-condensable impurities like hydrogen, nitrogen, or argon, depending on the amount, but the effect that they have is that they enlarge the two-phase region of the mixture, no? And obviously, the more impure that you have, for example, the hydrogen causes more the bubble point of the system to higher pressures, and it's also important to know because we don't want to operate. If we don't want to operate in two-phase, the more hydrogen that we have, then the higher pressure that we need to operate. Anyway, so I think the message here is that the impurities are important to know, and even at what we call a parts per million level, they have an impact, and we need to be aware and to be able to model that. Anyway, I think we think that the safe operation of the CO2 transport systems begins with a design that establishes the source of the compositions and the conditions that provide the appropriate safety margin. And the thermodynamics, I think, from my point of view, is the umbilical cord of the process modeling. And this is when we started asking questions. For example, what is the best model or the best equation state when we want to model the CO2 with impurities? And I think really there's never I don't think we can answer that question because it really depends on the chemical nature of the compounds. It also depends on how the model and the results of that model is going to be used, and the implementation. So where is the model implemented? But after all, I think all the models, or all the thermodynamic models, they're going to have limitations. For example, we're going to have failure near the critical point, which I think I saw clearly in the previous presentation on CCS. Jens showed some phase envelopes that I could see that close to the near critical point, there was a failure, or at least there was the lines were not joining at the critical point. We're going to have perhaps poor liquid density predictions. Some models are going to be computationally expensive. Also, we're going to have problems with compatibility between different softwares and etc. And ideally, when we have the models, I think we should be able to tune with experimental data. Unfortunately, for CCS or for CO2 mixtures with impurities, I think that data is very scarce. And I think that brings me to the thermodynamic consistency. We want to ensure consistency through the nodes of the CCS system, because what we don't want is that we have, for example, a plant that captures and compresses X amount of CO2, and then the pipeline that is being modeled with a different, perhaps, software platform and with different property package, we're suddenly designing for a different amount of CO2, and then the reservoir, because it's a different platform also, suddenly we are storing different amount of CO2. And I think we have, probably I didn't put it here, but we have been, or some people have done some modeling work showing that when we have these subsurface and surface segregations leads to discrepancies, like the ones that I noted here. And I think one of the reasons is because around this, well, we know that the physical properties of CO2, they change quite rapidly. A little bit of change of pressure or in temperature, we have suddenly a lot of changes in density. So we suddenly were operating around this area, and we start kind of we don't have a system that is thermodynamic consistency. So when we transfer information from one, for example, from one package to another one, that's when we're going to have serious discrepancies. And one way that we manage this integrated, or that we manage thermodynamic consistency is using integrated modeling. So one tool that we are using and we're starting to use a bit more is a software called Maximus. This is what we call as an integrated production modeling, which initially was developed for oil and gas applications. This is a software that is now is developed at KBC and uses as a software multi-flash, and so connects to Petrosim. An idea, so it's a rigorous pipeline and well thermohydraulics. The tank or the reservoir can be represented as a tank model, and it provides us life of field simulation. So that means we can model, I don't know, 30 or whatever amount of years, and it's a steady state simulator, no? And this is one way that we can actually ensure consistency. If we use, for example, multi-flash as our PVT simulator. Another thing that we are also using now here in PACE, or we're starting to develop, is something that we call digital twin. In reality, it's a digital tool, but anyway, so it's a digital tool that models the entire system. So it's integrated. We integrate surface and subsurface, not that dissimilar to the way that Maximus is doing. So also we have here, we don't have tank models, we have lookup tables. From these lookup tables are obtained from rigorous reservoir simulations that we get from clients. The pipelines and the wells and the compressors, things like that, are the physical sort of mathematical representation. So there's first principle models. This implementation is, and also the important thing is that the thermodynamics, we read the lookup tables that we generate from, in this case, we use multi-flash as our package, but we don't read the way that we interface with, we don't interface directly with multi-flash, so we interface with lookup tables that we generate from multi-flash. With this allows us to quickly understand the full chain operability, what is full chain modeling, and it provides most of the times a very intuitive big picture for regulators and management. And this is a product that we're doing in collaboration with ABB. So eventually this is going to go into their control systems. And the other project that we are doing, and we just started, I think, in May, I think, is a project called CCS Twin. It's a Eurostars project. And in this project, which I think is 2 years, the plan is to redevelop all the process models. I think the plan is to do it in July environment. This work is in collaboration with Hafnium Labs, which I think they are in the code. So we're going to develop, let's say, the process models, and Hafnium is going to develop, or we're going to connect to QProps somehow. I still don't know exactly how, although we haven't discarded just yet the use of Cape Open. So that's still kind of, I don't know how we're going to do it just yet, but it's something that we're starting to look into that. And the roadmap, I think for future is that I or we in PACE, we have to convince partners or clients on the advantages of Cape Open, particularly when we have existing Cape Open compliant software. I think in oil and gas, I think most of the clients are in the upstream, so they don't know much about Cape Open. So I have had maybe the last 3 years, every time that I've been asked about, they ask me, can you develop a thermodynamic model of my system? And I deliver a multi-flash thermodynamic model, and then they say, how do I use it? And then they say, well, where are you going to use it? And then they say, oh, we're going to use it in HYSYS. And then, of course, or they say, what is question instead are you recommending? So I say, for example, CPA or whatever, and then they realize that their HYSYS don't have CPA, or it's a completely different implementation. So they start asking questions of how do I use it, because it's not giving me the same results. And they always say, well, if you want to use exactly the same thermodynamic model that I deliver you have to use Cape Open, because otherwise you're not going to have the same results. And I think in upstream, there is a lot of companies that they don't have that capability. They don't even have heard about Cape Open. And the other important thing is about licensing. So sometimes you deliver something that we have licenses, but maybe the client only have one license of one product, so they cannot actually use Cape Open. They cannot interconnect different pieces of software. No? So that's also an issue. So I think from our part is to really to collaborate more partners, to educate also clients about the advantages of Cape Open. And internally, I think we're going to start now our own capability, I think, to develop Cape Open compliance. So that means that we need to start perhaps at least reading the specifications of the units. Yeah, that's I think the only thing I have at the moment. As I said, I think we're going to start our journey into Cape Open. So I hopefully if next year I can show you something more. And I think that's it.
Thank you, Eduardo.